The following program is brought to you by Caltech.
Hi, everybody. I'm John Preskill. I'm a physics professor at Caltech, and I have the honor this evening of introducing tonight's speaker, my friend Jeff Kimball. So welcome to the first Watson lecture in the age of Obama. And in keeping with the historic moment, we have for you tonight an appropriately ambitious, challenging, and forward-looking topic, the quantum internet. But before we get into all that, I'd like to see a show of hands. How many of you have heard of Lubbock, Texas? Oh, quite a few of you. How many of you have been to Lubbock, Texas? Oh, quite more than I expected. Well, everybody should know about Lubbock. It claims to be the 11th largest city in Texas. Never been there myself, but it would be nice to go someday because it's the hometown of two of my personal heroes. One, of course, is the immortal Buddy Holly, whose career had such a deep influence on the early days of rock and roll, and the other is tonight's speaker, Jeff Kimball, whose career has had a deep influence on the development of quantum information science. So even though it's bequeathed a lot to the world, Lubbock sometimes doesn't get the respect it deserves, so I'm going to sprinkle the introduction with some references to Buddy Holly, and we'll see whether you can catch them all. Yeah, that'll be the day. No, really, it's so easy, so easy. Maybe this isn't a Buddy Holly crowd. You're so square. Anyway, getting back to Jeff. Jeff, a blue-eyed, handsome man, studied physics and played basketball at Abilene Christian University, a few hours from Lubbock, and received a BS degree in 1971. He spent his graduate student days in Rochester learning the game of experimental physics. He received a PhD in 1978, spent a couple of years at General Motors Research Lab, and then joined the faculty at the University of Texas at Austin. And in 1989, he left Texas behind finally and came to Caltech, where he's now the William L. Valentine Professor of Physics. So like Buddy Holly, Jeff is a visionary who's transformed his field, in his case not rock and roll, but the study of how atoms and light interact and how they can be used to store and process information. One early achievement of his group was creating squeeze states of light, which are in a sense even darker than states with no light at all. His group has also demonstrated that a quantum state of light can be teleported from one side of the laboratory to the other side without the light actually passing in between, a trick that uses a delightful feature of the quantum world we call quantum entanglement. So Jeff relishes the challenge of doing really hard experiments that less courageous physicists shy away from, and remarkably, he and his team succeed time after time. So naturally, I've been looking forward to tonight's talk every day. It's getting closer. And finally, it's here. All right, that's enough of the Buddy Holly stuff. It doesn't matter anymore. So I'm glad that's over. We can get on to the serious part of the evening. Before Jeff speaks, I'd like to mention that Jeff has agreed to stay in the hall after the talk. So if you have questions after the lecture, then you can come forward and Jeff will be happy to entertain questions here for a while. I'd also like to mention that the next Watson lecture, the second one of the Obama era, will be here 4 weeks from tonight on February 18th, and that's also an appropriate topic for the new age. The speaker will be Harry Gray, the Arnold Beckman Professor of Chemistry at Caltech. The topic is powering the planet with solar fuel. So this is one that I think we're not going to want to miss, folks. And I'd be remiss, I think, if I didn't mention that aside from being inspiring to physicists, Jeff's work has also inspired poets. And there's one poem in particular that seems appropriate to read tonight because it has to do with tonight's topic, which is the quantum internet. Professor H.J. Kimball is much larger than a thimble and a veritable symbol of the physicist today. Could it be prodigious height explains his knack for squeezing light, or is Jeff's mind extremely bright? I guess that's hard to say. Jeff wants to build a quantum net. It seems quite hard, but still, I bet someday we'll get there. Just not yet. There will be a slight delay. At least they made a quantum node. That's a step along the road. They showed a photon could be stowed and then released, okay? Jeff's students stay up very late and try to share a quantum state between two nodes, but when you wait, entanglement decays. Once entanglement is strong, and they can make it last quite long, one node could be inside Hong Kong, the other in Bombay. And once the quantum net's begun, we're going to have a lot of fun exploiting work that Jeff has done. Here's what he has to say. I present Jeff Kimball.
Thank you very much, John. That's a hard act to follow. I'll try to redeem Texas as I go. I grew up in Texas. I'm proud of it. And in spite of the recent years, I try to demonstrate that there is competence in that state. So this is what we're going to talk about. I'll get around to explaining some more complicated things. But let me begin by trying to just tell you what maybe a lot of you know. The quantum realm is different. It's different than the realm that we inhabit with our senses and our personal interactions. It's governed by quantum mechanics, a spectacularly successful development of the 20th century. And it's the basis of kind of science, quantum mechanics, from chemistry to the properties of materials, both old and new, to new states of matter. This is a Bose-Einstein condensate from a group in Boulder. So quantum mechanics is ubiquitous in science. It's also the basis of much of our civilization, of the technology that we enjoy, this laser pointer, the computer that's projecting talk. This picture would not be possible of the Earth without the quantum mechanics of the electronics and the communication systems on the satellites. Worldwide internet is little flashes of light propagating through glass fiber, a miraculous and explosive development in the 80s and 90s. But there's more on the way, microscopic and nanoscopic structures that make use of quantum mechanics in interesting scientific ways, but also will find applications in our society. So that story is going to continue, but it's not really the story. The story of quantum mechanics that I want to tell you tonight is beyond this, what I would say, traditional evolution. And it's something that's happened over the last few decades, but most wonderfully, I would say, since the mid-90s. And it's really the marriage of computer science and quantum mechanics to give rise to a new progeny, and that's quantum information science. And I believe it's really a genuine new field of science. And so to give you some idea of what's going on, there's classical computation as set forth by Turing in the 30s. And modern computational machines rely on these principles. And in some sense, all these machines are equivalent, from an abacus to the PC I used to have until my dog chewed a sprinkler and electrocuted it, to now the Apple that I do have. It's apparently the case, though, that classical computation, as set forth by Turing, and communication, as the edifice built by Shannon, is subsumed by quantum information in both computation and communication. And the foundations, very importantly, laid by Feynman in the early 80s here at Caltech, but others, David Deutsch, Peter Shor won the Distinguished Alumni Award a couple of years ago at Caltech for work that he did related to a particularly famous algorithm in quantum information. Quantum communication, Charles Bennett, Joe Broussard, Arthur Eckert, it's provably possible to do things in the quantum realm, which I'll try to describe as we go, that you can't do in here. So life out here has a set of quantum miracles, let's call them. The quantum miracles are algorithms. I mentioned Peter Shor's. Peter Shor's is some esoteric thing in number theory that none of you should care about, except it keeps your credit card transactions secure. And if I had a quantum computer, I could be as rich as some of the Lehman executives were. So there are other wonderful algorithms that indicate that there is this separation. Quantum systems can simulate other kinds of quantum systems in a way which Feynman first suggested, and then others, Seth Lloyd and others have worked on. I mentioned communication. If two people want to share a secret, The only way to do that with classical information is for them to meet and write down random string of numbers and then separate, and then use those random strings as one-time pads to encode secret messages. But in quantum mechanics, the world of quantum information, it's possible to actually, for two people to share a secret, even though they're remote. All of these require new kinds of quantum machines, quantum capabilities, and for some years it was thought that such machines would be impossible because they would have to be too perfect. Peter Shor, the same Peter Shor who was an undergraduate here, and Andrew Steen in England came up with error-correcting codes, or classical error-correcting codes, and they discovered that there's a quantum analog, and John Preskill was famously successful in demonstrating that such things could be wound together to in principle at least, build machines that operate on quantum mechanics that would not otherwise be possible in the quantum realm. So part of that story of quantum information science is to ask about quantum networks. Any kind of thing, whether we're going to talk about it algorithmically, that there's in some kind of imagine, theoretically, or build things, we're going to have parts that talk to each other. A quantum node is going to be a place where we're going to have some kind of quantum system. I'll describe it, but you could just think about electron spins as fundamental particles that could interact, where information is processed, just like in the processor on the computer, and then stored. Parts of the computer have to talk to other parts, and so we're going to need channels. In terms of an internet capability or a quantum network, my computer can talk to other parts of the campus and other parts of the world, but only sends classical information and only processes classical information. So this picture is something really quite distinct from the normal way the internet sends messages and computers do processing. So if we're going to get busy trying to do that, it would be interesting to know, well, is it going to work? I mean, it's going to be a lot of work, and is it going to have some kind of capability, never mind it's going to make us wealthy, but would let us do things that we can't do in the classical world? If the answer is yes, well, that's great, but how are we actually going to know that as we develop quantum information science? It actually turns out to be an intellectually very challenging and largely unsolved problem for networks like one as simple as this, but imagine more complicated networks, to at some moment say, hey, it's been running, either on a theorist's notebook or in a laboratory. Is it doing anything interesting? How does one find that out? That's a hard problem. Experimentally, well, we have to turn these little cartoons into real things. And so how are we going to do that? What kind of physical systems, dynamical systems that do things, pendula oscillate, electronic element spark, can we use that to build these things? And as we build them, can we begin to implement interesting protocols that are going to be the basis of both computers? A computer is a very complicated network on the small scale, or on the large scale of a city or a nation. Can we let nodes like this communicate with each other? And one that I'll tell you about in a little while is something called quantum teleportation, which in cartoon form takes some kind of thing here, destroys it, and sends it somewhere else. So we'll talk about that in a little while. A broader perspective on this whole story, other than, okay, it's information and physics can help information science, is to ask, okay, well, what can you do for me, information science? What can you do for physics? So imagine an interesting thing to do to a physicist is to measure something. So this is a node of a network, this is another node, and we have something in between, and we want to know, well, did somebody walk in between or not? What are the limits to how well we can make such a measurement? Think about this as a GPS satellite sending something down to the ground, and in between, one of the fundamental limits to how well, practical limits to how well GPS works is the ionosphere. What is the best strategy for measuring the characteristics of the ionosphere and correcting them? The GPS network is itself, or array of satellites, is itself a network, but it's dynamically moving, and one needs to know where all those satellites are. What are the quantum limits to telling where are those satellites? We'd like to know that. So for quantum interferometry, clock synchronization, that is to say the GPS network, gravity wave detection, get rid of M and ask if space itself stretches and compresses. We'd like to see that in the LIGO project, for example. What are the limits for sensing that? And some of the most important work in this area was done by Vladimir Berginsky at Moscow State University, who is a longtime colleague and of this early pioneer as well, Kip Thorne at Caltech. So the roots of quantum information in terms of how well can you measure things, quantum information science, have strong origins at Caltech and now are being carried forward by a new generation of young people, Rana Adhari and Yanbai Chen. So measurement, well, what about communication? If you want to communicate A to B, you know you need bandwidth. So when everybody started out with this modem that your teenagers wanted to use, and it was infinitely slow to see anything like an image, so you get more bandwidth. So the story of why it's more fun at home for your kids is the bandwidth goes up. So let's just pursue that to its kind of crazy conclusion. A frequency, that is frequency spread, means energy in quantum mechanics. We'll talk about that. And as the energy, the bandwidth you want to use to communicate goes up and up and up, the energy goes up and up and up. And at some point, you have to take that into account. And Seth Lloyd here, who now at MIT, but was a postdoc at Caltech and an early pioneer in this area, asked the question, what are the limits when you think about physics for communication? And it turns out that the limit is you put as much bandwidth, the energy goes up and up and up, so that the little blobs that you're sending, not light pulses, but little blobs, are on the verge of becoming black holes. And when that happens, just on the verge, you don't want somebody sending your home video system black holes. And in that case, you can communicate at kind of 10 to the 43 bits per second, which is pretty good. So there's a good future ahead. Another perspective on, apart from this algorithm and security, is to think of a network as this quantum node and this quantum channel, and to say, well, look, this is some kind of I suggested you think of an electron spin, and there's another electron spin down here. How can those spins interact? If they're this far apart in their electrons, they just don't interact. They're so far apart. But the channel here, if I imagine exchanging photons, we'll talk about, that channel allows them to interact. So I can have interactions mediated by photons. And that, in the spirit of Feynman's original suggestion of how one kind of system can simulate another kind of system, quantum mini-body systems are things like superfluids, superconductors, Bose-Einstein condensates. You should think of this network as another kind of very interesting and complicated physical system, never mind its algorithmic complexity. On the other hand, its algorithmic complexity might tell us something very interesting about what kind of physics you can do. So, this is a painting by Turner of Hannibal crossing the Alps. And the point of this is to say, okay, that's all nice in PowerPoint, and it looks like these guys know what they're doing. You know, there's these theoretical things, or maybe some experimental possibilities, and we're marching down the yellow brick road to the brave future in Oz. Well, it's really more complicated than that. It's an explosive time of development and experiment and theory, and nobody really knows what's going on. Fortunately, these soldiers had the great military tactician Hannibal himself. And equally fortunate, we have a great qubit theoretician, Professor Preskill, who directs the Institute for Quantum Information, a theoretical enterprise of great success here at Caltech. He's joined by Alexei Katayev, Leonard Schulman, Gil Raphael, faculty members here. And although they do a great job, and I don't want to say anything disparaging, I would like to point out that if you look at this in detail, theories over here, this you can't quite see, elephants at bottom move to top in theory. In experiment, elephants are much more difficult to deal with. That's experimental science. So what we have to do is somehow, what's the real story that underlies these theoretical ideas? And I want to try to tell you a little bit about that. We have to go in the lab. We have to talk about real physical systems. So let's get real. So this, imagine, is one node in a network, and the question is what's inside of there. And I want to try to tell you, not in its great experimental detail, but in some sense that you'll have maybe, it tasted kind of good. I don't know what was all in it. What kind of things we can use. And everything I'm going to tell you about relates to coupling atoms and photons. And so this is a complicated picture, and we're going to get around to explaining it. If you think of this as a network, these are little elements of a node, and there's an atom. And this atom is going to allow us to take its quantum state, turn it into a photon. The photon's going to propagate somewhere else, and the information about the quantum state is going to be transferred to another atom. It sounds kind of complicated. It's a protocol, I believe, the first real physical way that one might realize these quantum networks that was carried out by this set of people a little over a decade ago. And so I want to get up to speed to try to kind of explain how that might work. So we have to talk a little bit about atoms. Atoms are part of the story, and we have to talk about photons. So, atoms. Quantum mechanics has certain things to say about atoms. Cesium is one that's going to be important to us. It's really a mess. This isn't about atomic spectroscopy. This is about, let's look in some little small corner and see if we can understand something simple. So what we're going to do is look at one particular transition in cesium. This transition is the lowest level. This is energy going up. So the lowest level, the electron closest to the nucleus, is here. And 1 unit up is here. And 1 unit is 852 nanometers. So the electron can sit here, be in the ground state, or it can sit here, be in the excited state. And although it's cesium, it's familiar to you. Cesium is just like sodium. And so the yellow sodium street lamps are transitions between these two levels, and that red line would be yellow. So we're going to use those two levels. Atoms are wonderful, though, in the sense that the electron could be in the ground state or it could be in the excited state. Well, the electron can be in both states at the same time, and that's called a quantum superposition. And that's important about atoms, and I'll make use of that as we go. This wavelength, 852 nanometers, red light is 600 nanometers. This green laser pointer is 500 nanometers. This is just beyond where your eye can see, so it's red radiation. And that's not so important except to set the scales for things. It's almost visible radiation. Now what about light? Light may be a little bit less familiar to you. Light is an electric field that is a function of space, runs along in this running wave, and the electric field oscillates up and down. And if we look in space at one snapshot, the electric field is bright, dark, going up and down, and the wavelength is 6 times 10 to the minus 7 meters. That is to say 0.6 microns or 600 nanometers, where a human hair is about 100, 200 times thicker. So this is a small scale for the wavelength. How fast is this thing really oscillating up and down? If you sit somewhere like in the ocean and you bob up and down as the waves go by, how fast would you be bobbing? This thing, you would bob every 2 times 10 to the minus 15 seconds. That is to say, the frequencies are 10 to the 14 hertz. And the ratio of this length scale to this time is the velocity, and that's just the speed of light. And the speed of light is 300,000 kilometers per second, or 186,000 miles per hour. So it's hard to do in PowerPoint, but these things are running at that speed. So we'll slow everything down for the discussion. So that's a so-called traveling wave. How does that wave interact? We want it to interact with, finally, an atom. How does it interact with a charge? The electric field times the charge gives rise to a force, just like gravity. It's a vector, but not a scalar interaction. So a charge in an electric field feels a force, and it'll move. So in terms of what we had, this running wave of electric field running in space, a charge sitting there just goes up and down as the electric field runs by, just like a cork on the ocean, more or less. It feels a force. Something else important happens, though, and that's that the power radiated by this charge goes as intensity. So as it oscillates, little bursts, little packets of light in classical electromagnetic go flying out. So this wave, as it goes by, loses energy to accelerating the charge, and that energy is radiated by the charge. Now let's put that light wave in a cavity. So we need a mirror, and we need another mirror. Just think of these as 2 frets on a guitar, and we're going to hold the string down. And inside of there, then we put not a traveling wave, but a standing wave. So in this thing, just like a guitar string oscillating back and forth or a drum head, the pattern is stationary but oscillates up and down in time. And the charge goes up and down. It radiates just like before, sends out little pulses of light in different directions. And that's a problem, but that's how the charge interacts with the electromagnetic field. Now, how do we turn that into a quantum story? Well, that happened in about 1899, quite a while ago, by Max Planck, and his hypotheses about light quanta made much more secure by Einstein and others. And then these gentlemen in particular won the Nobel Prize for the theory of the quantum theory of light, quantum electrodynamics. Let's apply that theory to just our single mode of electromagnetic field. It's oscillating up and down. That's the classical picture. It looks just like any kind of classical wave. And what quantum electrodynamics has to say is, no, the cavity field is described by this no photons, one photon, two photon, where the energy between these two possibilities is just this famous quanta that Planck and then Einstein introduced. It's these one ladder up is called one photon. These are the little corpuscles of light, now in the context of a cavity. And what this story says is this is the real description of the electromagnetic field. It's kind of hard, though, to think of this and that at the same time. This is just this ladder. You sit here, you sit here, you sit here. You got 1, 2 photons, 1, 2, 3. How does that do that? So going this way is kind of hard to think about. And thinking about it is worthwhile. Roy Glauber thought about it in the early 60s, and it earned him a plane ticket to Stockholm in 2005. And I won't tell you in detail what he thought about, but it's that this ladder, this picture, and this picture really are the same. We just need to know how to distribute the amplitudes for the photons. This distribution, as drawn, is the same, describes the light bulb that's shining down on me now, so-called thermal distribution. What I'm going to be interested in is learning how to take no photons, that's easy, nothing, and then just pop in 1 or 2, so discrete. Control over this ladder of a wave which hadn't existed heretofore. So now we got the two parts. We've got the atom. It's got 2 energy levels. This is low energy, this is high energy. Energy goes as frequency because Planck told us. We couple that to this thing I showed you about the cavity. That's quantum electrodynamics of the field that lives inside the cavity. So the photons are going to be here, the atom there. What do we get? Well, that's a problem to solve in quantum mechanics. It was solved in 1963. And what you get is an energy level structure this is no quanta, this is 1 quanta, this is 2. It's not so important the structure of that in particular, except to say, hey, I took something and atom, and I coupled it with photon, and I made a molecule. Chemists do this all the time. They're really proud of it. And we're going to do that too. This is a molecule which is effectively an atom bound to a photon, if it were in this level state. This is an atom bound to 2 photons. What's the dynamic? That's the structure of how atoms interact with light. That maybe doesn't tell you so much if you're not a physicist. Let me give you another. What are the dynamics associated with that level diagram? Here's an atom in an optical cavity, the light's bouncing back and forth, and the atom is coupled. That's what the G means, and we'll get around to explaining more. Let's start with the atom in the excited state. So now all the excitation's in the atom, so the big blob means all the excitation. 1 quantum's in the atom, and nothing's in the field. This is the cavity. And now we turn on the interaction. What happens? Well, it goes away. It leaves the atom, and it excites the field. Now it's back in the atom. So now all the excitation's in the atom, and at this moment, there's 1 photon in the field. And so what happens is the excitation is going from atom to field, atom to field. It's not flying out into space. It's a nice reversible process, which you can understand if you think of the atom and the cavity as 2 oscillators that are coupled. And I hope that picture is familiar to you. Have you ever built kind of stuff like that? You can look at this and see. Now it's all in the atom, and then it goes over in the field, and now it reverses. Now it's all in the field, and now it's going back to the atom. Why does that oscillate back and forth like that, the atom and the cavity? Because they're coupled. What gives rise to the coupling? Well, there was a charge that feels the electric field. An atom is an electron and a nucleus, so the electron goes one way and the nucleus goes the other, plus and minus charge. And so the oscillation you get of the atom is this force of the electric field pulling the electron one way and the nucleus the other. And that gives rise to this G, and there's a microscopic, I could show you the answer from quantum electrodynamics. But the important point is, if we can make that coupling big enough, these photons flying out that are taking away energy won't be part of the story. We'll just have this nice reversible interaction that we can control. So that gets us through a quick primer. I've introduced the cast of characters. We've got Adam the atom. Adam is going to look it depends on the makeup, but he's going to look like this or like that in the cartoons that follow to tell you things that are going on. You've seen Phoebe the Photon. Phoebe comes in 2 kind of schizophrenic forms. There's Home Alone Phoebe, a fairly reclusive. She lives between 2 mirrors like this and is happy to be there. Never mind. There's also flying Phoebe, who's kind of out and about, socialite, flies around at the speed of light. Well, these two actually, flying Phoebe and home alone Phoebe, can interact. What if home alone Phoebe wants to go out? All we have to do is change the reflectivity of this mirror, and the photon that's in there can go out. So home alone Phoebe can actually fly out into the world. What do these pulses really look like? Well, they look kind of like this. Have these cartoons of these little pulses. It's propagating electromagnetic field, but subject to these rules of quantum mechanics about this ladder in discrete quanta. And the point now is to try to understand, we've got Atom the atom and Phoebe the photon. How are we going to let them interact to do interesting things in this particular setting of the lecture tonight for quantum information? Before I go on to say anything about that, though, let me point out that pulses like that have a really powerful role in other areas of science, not just one quanta, one atom that I'm telling you about. Professor Ahmed Zewail has pioneered the use of these to watch molecules, to watch chemical reactions take place. He directs Center for Ultra-Fast Science and Technology, looks at dynamics, structural changes, really interesting things from solids all the way to things of biological relevance, protein folding. But we're going to stick in this one atom, one photon kind of domain. And having said that, I think I should introduce you to Atom and Phoebe. This is Atom, and there's Phoebe lost over there. And the goal is to let Atom and Phoebe interact. So go for it, guys. When they interact, somehow, we want them to get excited. And when they leave each other, that's enough. When they leave each other, we want them to carry away a part of one with the other. And so the question is, how do we let them interact? How do we do all that stuff? How do we come to this coherent interaction? Well, the idea is, here's an atom in a cavity, makes a photon, the photon leaves and comes back. So we want to use this atom in a cavity as a paradigm. I told you I can turn on the coupling, and the excitation from the atom can go straight away into the cavity, not out into free space. I didn't tell you I can time reverse that coupling so photons from the outside world can come back in. It's also possible to use the atom cavity system so that if two photons should arrive, one of them is sent back and the other one goes through. So to have nonlinear interactions mediated by just a single atom. This is what one of the cavities really looks like here. This dimension is about 1 millimeter. It sits inside a vacuum chamber. It's a really nice set of mirrors. The light bounces back and forth about 500,000 times. So when a photon's in there, if you've ever been in a hotel and you look and you count the reflections, it's the first thing I ever do. And you count, oh man, you can see 10 of yourself. I have a postdoc who was just visiting from Israel, who's now in the Weissman Institute. He said, you can't believe it. I was in a hotel, I could count myself 20 times. So that's exciting to some of us. Somehow we've trapped an atom inside of there. We've done it with this cesium I told you about, and this rate where you could see the excitation going back and forth was happening in a few seconds in the movie. For this atom in the cavity, it happens at a rate of about 30 million times a second. So things speed up in this experiment. The atom's pretty well localized. It's localized for a few seconds and along the cavity axis to 10 nanometers. Which is, 100 times the diameter of an atom. It's actually in the lowest ground state that's allowed quantum mechanically. And it's taken a while, and the thing I want to emphasize most is not necessarily the science, but the people who actually do these things. It took a long time to learn how to do this with David Verneuil Junier and here Christoph Nagler, here Jason McKeever and Joe Buck, graduate students at the time. It's hard work, it's thirsty work. A more recent cast of characters, Kevin's up at JPL, and the most recent cast, Tracy's now in Innsbruck, Dal you'll see running around the stage up here, and a little while, and Eric's an undergraduate at Caltech working on this complicated apparatus. So this is supposed to remind you of two nodes in a network. Baby steps. We're going to try to take a quantum state. What's a quantum state? It's a superposition of states in an atom. This is the transition I've been telling you about. That's the 1 electron volt, 800 nanometers. Atoms also have nice ground states. This is the basis of the atomic clock, the so-called hyperfine structure in an atom. We're going to make a state in the hyperfine structure. We're going to turn on a laser, and we're going to turn that state into a photon. And away it flies. And we learned how to do that over the years, to do this pretty well. Having made the photon, that seems kind of easy compared to the other part. Now we've got to catch it. And we don't want to catch it, just destroy it by putting it on black paper. We want to catch it and have it reversibly, coherently saved. And so it won't be obvious necessarily if we made it by doing something here, just do the time reverse version there. And that actually turns out to work. And so if we just take whatever pulse shape we used here to make the photon, we can do the time reverse pulse shape there, and the photon will pop coherently back in the atom. And a year and a half ago, we actually demonstrated that in some detail that you don't want to know about, except to say it worked, it's coherent, wasn't perfect, and we're still working on it. Okay, how do we know in the lab that these are single photons? These single light quanta, very small energy, just the amount of light that's flooding me now is too bright. They wouldn't turn it down, but anyway, it's 10 to the 21 or so photons per second. That's a lot of photons when you want to do one. So how do we know it's really one? Well, I want to convince you, independent of any detailed knowledge of what's inside, so I'll put it in a black box and say, okay, try to make a photon. Well, that detector clicked. Should have. Oh, that one clicked. What's the likelihood that both detectors will click? Well, if it's only one photon, there's only one quantity to be absorbed, so it should never be the case that one photon, that both are click. So with one photon, if we do this over and over and over, we should never see two clicks here, but it's okay to have a click here and then a successive photon have a click. If I, by contrast, turn this laser on and off, the cross correlation for that kind of light using the techniques that Roy Glauber or George Sudarshan introduced should look like this. And this is what we actually see. There's hardly anything there. I can explain in detail why there's a little bit. Nothing's perfect, but the two photon events, the contamination of this one glorious Phoebe running around is down by about 150. So it's a beginning in terms of moving coherently quantum states from place to place. This is the lab, however. So this is the simple story. That simple story is supposed to be put together to make that. This simple story turned into this when we really did it. That's kind of complicated. And I'm not sure that you're willing to invest in my company to say I need one of these labs for each one of those nodes. So in fact, whoa, man, this is too complicated. I'm never going to believe that. Now, if you're from Texas, you know what whoa means. If not, John Preskill, somebody should tell him. So what are we going to do? Well, a few years ago, Kerry Vahala and I undertook a project to come up with a new way to do this, new way to do business. And it's based on something that Kerry already had pioneered, and that's a little donut of fused silica. And this is a wonderful donut. It's a torus. It's so wonderful that light can run around this millions of times before it decays. And I could tell you about these modes. They're the optical equivalent of whispering gallery modes. The idea of using structures like this belongs to Vladimir Burginsky, who I mentioned earlier, but the genius to create these is from Kerry Vahala's group. And what we want to do is put one atom right there. We want to put it about 200 nanometers from the surface, and that's going to be the little element inside those boxes where we make a quantum network. So how are we going to do that? How do we accomplish such a heroic task? Well, we need some wizards from Oz and the quantum optics lamp. So let me explain a little bit about how we're going to do that. So let me just show you what we're going to try to do. You see on the screen the little toroid. We're going to try to show you how you put an atom there, and then we're going to let Phoebe and her friends, well, they're all the same photons, fly around. So now how do we do that? The first thing we have to do is atoms, we have to cool them. So let's cool the atoms. These are atoms. They're hot. They're running around like the room temperature. And now we're cooling them. Cooling them. There's cooling light. They're getting colder. They're getting colder. They're getting colder. And now they're cold enough that we can get a stick, reach in there and get one of them, and move that atom over to the toroid over here. We get it near the toroid, and when we get it there, we cue the photon, Phoebe. And Phoebe runs along this tapered fiber, which was pioneered by Kari Valhalla and Oscar Painter, runs around. Every time it whizzes by the atom, it goes whoo, and they get interact, and they get excited, and entangled is what I want to say, but I'm going to get to that in a little while. Okay, then we try again. In comes a photon, Phoebe, starts its transit around the circle, it comes near the atom, It's experimental physics. Okay. Undaunted, we send another Phoebe. Phoebe circles around, gets around, circles around. It's so exciting, that atom, I know. And comes flying out. And that's how we're going to do it. Okay, so let me show you in a little more detail as how we're actually going to do that. Again, people are important. They make the whole world work. Here's an apparatus I'm going to tell you about. These are important people, Takao Koi and Barak Dayan, and this is work done in collaboration with Kari Valhalla's group and a cast of characters I'll show you as we go. So in this apparatus, well, now on a new apparatus built by Takao, Daniel Elton, and now Nate Stern, we're learning to do what you saw on the stage. And what did you see on the stage? There is this little strip, courtesy of Kari Valhalla and his colleagues. It's this army of toroids that we're going to send out into the world like a plague to take over. And what we need to do is trap an atom there. So this is real. The atom, of course, is PowerPoint. It sits in an evanescent field. This is a real picture, except for the atom inside. This is the tapered fiber. You can just see it here that brings the light in and out. And we've done an experiment where we send photons in, sometimes in pairs, and only one of them is able to get out. Where do the atoms come from? Here's a cloud of atoms cooled to about 10 microkelvin, a part in 10 to the fifth of absolute zero. Here's the taper. We drop the atoms, and when we drop the atoms, they fall by the toroid. That's an absolute defect. I'll show you how we try to do what's in the skit, but we haven't done yet, to nail one of the atoms right there to interact. And when it's nailed there in this tiny little toroid, interacting in this evanescent field, a first photon flies by. When that photon flies by, we know, in fact, the atom knows it was there, and that atom's not going to let any other photon by. So any subsequent photon actually goes out the back door. You can't come through. The atom relaxes, lets a photon through, and then says, oh, one went through, nobody else. And so the second one goes like that. And on and on and on. Another photon can go by. This is photon transport regulated in an optical fiber. This connects to optical fiber in the lab, like telecommunications fiber. And the flow of photons through here is regulated by that one single scrawny little nothing atom. What's the time scale over which this regulation happens? It's about 14 billionths of a second, 1.4 to the minus 8 seconds. And it happens because of the way the atom and the cavity field interact. So we're trying, as I said, that's the one step in it. We're trying to learn how to do not 1, 2, 3, but several of these to actually build internets. This is work by Cindy Riegel and Scott Kelber. And we want to take special light traps. Here's a light trap with a bunch of atoms, catch one of the atoms and move it next to the surface, as you saw here with the atoms circulating around, and we brought up a stick. The stick is a light stick, a focused laser beam and bring it near the surface. And we'll do that with special structures that we are collaborating with the group of Kerry Vahala and Oscar Painter to learn how to do these kinds of things. But I should say we all owe a debt of gratitude to the pioneering work of Amnon Yariv over many decades here at Caltech. And the kind of things we want to do are, these are the toroids I've showed you that we already know how to do. There are new kinds of toroids being fabricated by Kerry Vahala. Even more complicated for reasons I could elaborate, toroids by Kerry Vahala and Oscar Painter, and new kinds of structures that aren't this, but something yet even more miraculous, so-called zipper cavities by Vahala and Painter, which have now dimensions not of 10 microns, but hundreds of nanometers, so below. And these are the people that are doing this trapping experiment that I mentioned, Scott Kelber and Cindy Regal, trying to do what you saw up here, put one of those atoms on a stick so we can put it where we want it. Okay, so back to quantum networks. We're going to start small. You recognize a small state, that's actually to scale. And build a quantum network. And then we're going for the big time. Here's a quantum node over long distances. What's the basic paradigm? We're going to entangle. We need to entangle these nodes. I'll tell you what entanglement means. It's something real important, real special. And having entangled two nodes, we're going to teleport quantum states from place to place. So that's the basic paradigm. What's the basic problem? Surely this is too complicated for Texans. You already know I'm from up here, near Lubbock. Tom Tombrella, whom I owe a great debt of gratitude, Kerry and I both, for helping us start this research program with the toroids when he was division chair, but both as colleague and as division chair has really made my life at Caltech really wonderful. So, as I said, it may be Texas, but we're back. Okay, quantum teleportation, what's that all about? Imagine Victor and Victoria. And Victor would like to send a state to Victoria, maybe a beam of light. These could be techies, for example. How's he going to do that? Well, he employs Alice and Bob, and Alice and Bob run a quantum internet company. They have a standard kind of channel, just a piece of fiber optic, but they have something special, and that special thing allows them to charge these really high subscriber fees. They're able to distribute entanglement between the two nodes in the network. And with entanglement, Alice and Bob can take this unknown state. Alice receives these two things, and the process destroys that state. Sends a message to Bob. Bob uses that information to manipulate this guy to become that state. And the miraculous things to note about this is nowhere in between did that state propagate. The physical state was destroyed. This could have been sent to Alice and Bob the day before. This is a classical channel which can't carry quantum state. So how did the state get from there to there? That's of interest. Also of interest is if Alice and Bob do this right, and Victor and Victoria can check, if they do this right, they know nothing. They learn nothing about the message in cryptographic terms, but in terms of a quantum state, they learn, in the limit that they do it well, nothing about the state, and Victor and Victoria can check. And that means that if Victor sends Victoria a state, and they've checked, they don't have to trust Alice and Bob. Victor sends a state, then Victoria can be clear and certain that it's really Victoria's secret. Okay, how does quantum teleportation work in the lab? This experiment we did about a decade ago. Alice is back here, Bob's back here. We sent a laser beam, it went in one place, hopped over about a meter, came out the other. And that's obviously, I think, important for quantum networks. And that particular experiment garnered some press. All of it was completely, really disappointing, except for the Comedy Channel. And they actually got it pretty well.
Seen on TV. First, this just in. No. I asked for a Bud Light. In California, scientists undistracted by social lives or hygiene have successfully constructed a teleporter that can zap a beam of light from one side of an optical bench to the other, which is great news for beams of light. We're sitting at the end of one bench and want to get to the other. Although scientists are overjoyed at their success in transporting a beam of light, they are perplexed at how the light's luggage ended up in Hawaii. But will it work on humans?
It certainly won't happen in the near future. I would be skeptical if it'll happen in the next millennium, if what we're after is teleporting people.
Kimball added, even if we were able to transport, say, a Captain Kirk, for example, we'd still have to ship his toupee and girdle UPS.
Well, so there's that did the best job of conveying the science of anything that was published about that experiment in the popular press. Quantum channel, 2 nodes, and for this teleportation stuff, we don't need these beams of light flying around all over the place. They're like children that have had too much sugar. Go lay down. So we need quantum memories, and if we can have quantum memories that are entangled in a way I'll describe now, we can do teleportation. And so how are we going to do that? So here's another example. What's inside of here? What's going to let us do interesting things? And what's going to be inside of there is something very wonderful, an ensemble, now not a single atom, but an ensemble of maybe 100,000 atoms. And in a protocol that was introduced by Lu Min Dewan, who was a postdoc here working with John Preskill and my group at the IQI, a really, I think, very important paper to show how to have remote quantum systems become entangled. And it really relates to learning to read and write. And again, in Texas, we learn that. We can write and we can read. And so reading and writing, we can create entangled ensembles. And how are we going to do that? The Wizard of Oz and our little munchkins. So come on up. So what I'm going to show you is now the simple version of how we're going to entangle the thing on the right-hand side, 2 atomic ensembles. So the basic idea, again, is a bunch of atoms, not one, but a bunch. There's a bunch over here on the left and on the right, and we're going to cool them off. So we need cooling light to cool them off. We use lasers to cool them. So there they are. They're getting cold. They're moving around, getting cold. This is 3, but it's really about 100,000. They're getting colder. They're getting colder. They're getting colder. Are we ready, Dal? So here are the cold atoms. That's a black box. You can't see it, but it's a black box. This is a black box. Okay, so now what we're going to do, the cold atoms over here on the left, it's on your left, they're on your left. We're going to flash some light on them, and some of that light, here, flash, boom. Some of that light propagates away. Come on, Eric. Propagates away over to the black box. And got detected. That's a click. And we're left behind with one excited atom. That one click, well, that means there's one excited atom. Okay, now what about here over on the left? We've got to cool these guys off too, so turn on some cooling light. Let's cool them off. They start out at high temperature, 300 Kelvin, room temperature. Cool them off, cool them, cool them, cool them. Takes a few milliseconds, they get cold, and then turn your lights off, you're not excited yet. Boom, out comes a photon from one of them. We don't know which one. There are 3 of them there. Any one of the 3, or in the experiment in the 5th, could have emitted. The photon propagates over to the black box where it's going to be detected. Okay. Now, so that seems pretty straightforward. The miraculous thing about this protocol I mentioned is, what if we flash both ensembles with light at the same time? There's one on your left, the atoms, there's one on the right on your atom, and now we're going to flash them at the same time. Now, you're not going to be able to see the photon propagate this time because I don't want you to know where it comes from. The previous example, you saw the photon. If you see the photon, well, of course it's there. No, if you see a photon, you destroy it. So the previous one wasn't really quite right. You're not supposed to be able to see it. So now what we're going to do is flash this guy, flash that guy, Photon could come out of either one, but you're not going to get to see them. Okay. Whoa! So what happened? Well, it came from one or the other. We don't know which. So it could have come from there, could have come from there. Which one did it come from? It came from both of them. We have to admit that possibility. And that's what I want to tell you about now, that these two groups of atoms become entangled from that process. Okay. So now, what's going on? We've got a bunch of atoms here and a bunch of atoms here, and we're going to flash some light. Let's do it one at a time. If I flash some light here, I can send a photon out and get an event, and of course I know it came from here. If I flash some light here, I can get a photon out, detect it, and I know it came from here. The world's completely different if I put a beam splitter there. This is 50-50. A photon goes here, it could go there, could go there. 50-50, could go here, goes there. And so a photon from here and here have the possibility both to go here, both to go there. So if we flash this, and one of the detectors clicks, we don't know in principle. It's impossible. It's just that we don't know. We can't know in principle where it came from. So what we know is we'd made a detection, and what we can infer then is that one atom was transferred. It was transferred from here, the photon came from, or it came from here. If it came from one of these, if it came from here, one of the atoms changed states. If it came from here, one of the atoms changed states. So the state we have to assign is the state where it came from here or there. And that's what's called an entangled state. The ensembles that you were seeing are the left and the right, a left and a right ensemble, and the photon could have come from either place, so the atom that's left behind is either left here excited or there excited. And that's one quantum of excitation stored here or here. And you ask me where it is it on the left or the right? Yes, it's in both places at the same time. This is familiar maybe from the first slide of the talk. This is one chamber, this is another chamber. The entangled state I described is an entangled state between this little pencil shape of about, it's a chunk of human hair long. It's 160 microns in diameter, a millimeter long. And there's an entangled state between these two, which is to say there's an excited atom here or an excited atom there. Where is it? It's at both places at the same time. That's entanglement. And the mathematical statement, the way a physicist would write it, is there's been a spin flip at one place but not the other. These are the people that did it, and this is what the lab looks like in the daytime with the lights on, but when the experiment runs it's dark. There are atoms over here, atoms over there, and they became entangled, so that there's one excitation symmetrized among all these atoms, one excitation symmetrized among all those atoms, and it's this entangled state where that excitation is either here. If it's here, it's not there. If it's here, it's not there. And you ask me where it is, it's at both places at the same time. Now, how we show that unequivocally, that no assumptions, we do measurements of these things, and without any kind of, trust me, whatever these insurance instruments are called, they're going to be okay. No, it really works without assumption. We've done other experiments to try to show that this entanglement between these two ensembles can actually be used for something. In this case, be used for two remote locations sharing entanglement to do secure quantum cryptography. We've been able to map propagating not one photon, but if the photon's over here and over here at the same time, we can map that into a quantum memory. We need that for a quantum internet. Leave it there, take this piece out, take that piece out, or take both pieces out. We've been able to do that, and these are the people who've done that. Way now at the University of Michigan, Garrett, an undergraduate here at Caltech, Kyung and Scott leading this effort. So, what's the grand view? Well, it's much grander than I've been able to say. I think the universe of quantum information science has lots of really exciting things. I think it's a revolution in our understanding of the natural world. I think it lets us retrospectively understand a lot of things that we didn't really have adequate footing to understand theoretically. It's a broad impact both on theoretical and experimental science. Just to give a couple of examples, Jim Eisenstein in his laboratory is pursuing a beautiful theoretical idea by Alexei Kitaev, a professor at Caltech, both these gentlemen, and Gil Raphael, assistant professor in physics, of exotic new quantum states of matter whose underlying understanding is topological and maps into areas of quantum information science. John Preskill, ever the nut, has been wondering since I met him what happens when you throw a book into a black hole. Is the information lost? Well, I told him go after it and see. But he refuses to do that. He just thinks about it, and by using quantum information, he's come up with Patrick Hayden with a completely different perspective on this problem, and I think a very exciting possibility. So there's a grand universe. If we come closer to home, an outpost in quantum information science are these quantum networks that I've been trying to describe. And what excites me most about that is not the algorithmic capabilities, but these are really our physical systems, I think, as we begin to build 2, 4, 6, 8 that have just not existed in nature before, and they'll be really exciting to explore. If we go down on the surface into the laboratory, well, it's an exciting frontier. It's an exciting frontier. We don't know how to get from here to there. I've told you some of the ideas. Some of the ideas relate to new kinds of nonlinear optics for controlling photons in collaboration with Kerry Valhalla and Oscar Painter. Ideas about how to send quantum states from place to place via quantum teleportation. Ideas about how to make teleportation work better by having these entangled beams not be flying photons, but entanglement we can store remotely in quantum memories. I've told you all this going back to the beginning kind of as a linear story like the Yellow Brick Road, as if we really knew what we were doing. It's a much more diverse and exciting time over the last decade. It's been one of the most exciting times I could have imagined in a career. This confluence of people, of theoretical ideas from computer science on the one hand, from experimental physics on the other, from theoretical physics, and it's brought together a really wonderful community on campus at Caltech across the world. It's really very exciting, but it's not this linear road. It's much more chaotic than that. Much more exciting, sometimes much more frustrating. But at the core of it all is what Francis Crick called the mad pursuit of science. It really is a wonderful way to spend your life. I can't imagine that I get paid to do this. And so with that, I think everybody has their own core of, man, this is so incredible in terms of science. The core of mine is the excitement of these atoms and photons interacting. And so I think what we should do now is turn off the lights and just watch the atoms and the photons. Thank you. Thank you. So I'm happy to take questions. Anybody who wants to come up, come on up.